Welcome to Electronic Geek. In this video, we shall be seeing about priority encoder. In the last video, we saw about octal to binary encoder and we saw that there was a major flaw in the circuit, which was if more than one inputs were high, then the output we were getting was completely wrong. So in this priority encoder, that flaw has been completely resolved. So we'll be seeing about priority encoder in this video. So let's get started. So in this video, we are going to see a 4 input priority encoder. So basically, the operation of a priority encoder is such that if two or more than two inputs are high or are selected at a time, then the input having the highest priority will be taking the precedence over the other one. So if you see in this 4 input priority encoder, we are having 4 inputs D0 to D3 and the two outputs x and y, which will be representing the number in binary, and there is one more output which is designated in V. We'll talk about this V a bit late. So if you see here in this truth table, we are having 4 inputs from D0 to D3. So the input having the highest number, this one, is going to have the highest priority. So D3 is having higher priority than D2, will have higher priority than D1, will have higher priority than D0. Also over here we are having the third output bit, which is represented by V. V is called as the valid bit indicator. Okay, so this output is always high when one or more than input is high. So let's check out the truth table. So the first case is all the input bits are 0, meaning none is selected. So when all the inputs are 0, there is no valid input and V is equal to 0, and under this situation x and y, that is both the output bits are don't care conditions. Now the next case is D0 is selected or D0 is high, meaning it has to represent 0. So it will be 0 0 and V is high, because for V to be high, at least one or more than one input should be high. Now the next case is D1 is high. Now this is a priority encoder, which means D1 is always going to have higher priority than D0. So the value of D0 should not matter, and that is the reason D0 is don't care. So that will be equal to 0 1, and again V is high. Same goes with D2. D1 and D0 are don't care for D2, because when D2 is selected, D1 and D0 will not be affecting the output at all. So it's represented as 1 0. Then coming to D3. So when D3 is high, all the other inputs, no matter high or low, that is why they are represented as don't care conditions, the output is going to be 1 1, which represents 3, and V will be high. So over here I have prepared one more expanded truth table. So if you are not comfortable for filling K maps by looking over here, you can check out this truth table and fill the K map. So this is done. Now K-map for X. So these were the values filled by checking the truth table, and the pairing for the same is done as this is taken as the first pair and this is taken as the second pair. So as you can check out, D0 and D1 are constantly changing for all these cases. So D0 and D1 will be neglected. Between D2 and D3, we can check for the first case. D2 is changing, so we'll ignore it. And D3 is same. Also D3 is equal to 1. So it will be equal to D3. For this blue colored pair, we can see that D0 and D1 are changing again. So we will ignore both of these. Between D2 and D3, D2 is same for both the cases and is equal to 1. So the final output equation is D2 plus D3. Equation for Y. So this is the K-map and the pairing is done like this. So for the blue colored pair, we can see that between D0 and D1, D1 is same, whereas D0 is changing. So we'll ignore D0, we'll take D1. And between D2 and D3, D2 is same, but it's 0. So it will be D1, D2 bar. And for this yellow colored pair, D1, D0, D1 both are changing, but between D2 and D3, D3 is same, so we'll take it. So the equation becomes D3 plus D1 D2 bar. Now the output equation for V. As told before, V is the valid bit indicator and it is only high when one or more than one inputs are selected or they are high. So the equation will be OR of all the inputs. D0 plus D1 plus D2 plus D3. Now we will proceed to Proteus simulation. I'll show you. So here is the circuit. So over here you can see D0 to D3, these are the four inputs. So D3 will be having the highest priority of all. And over here you can see that this represents the LSB, this LED, this represents the MSB, and this is the valid bit indicator. And the output to LED is connected through a resistor of 280 ohms. And we'll check by simulating the circuit. So when all the inputs are 0, these were don't care and valid bit indicator was 0. Now let's select this D0. So as the D0 is selected, the output should be 0, 0, and yes, valid bit indicator V is high. Now we will select D1 keeping D0 as high. So when we select D1, the X should be 0, Y should be 1. See, now we'll select D2. So it will be 1, 0. This will be 1, this will be 0. See, and in the case of D3, it is 1, 1. So as you can see, the output is not affected by lower priority inputs. So that flaw in normal encoders has been totally resolved in this priority encoder. I will be attaching a link in the description below through which you can access this document for your reference. So this is it for this video. Thank you for being till here. Thank you so much. Please do like, share and subscribe to my channel. Do give me your feedback in the comment section. Thank you for being till here. Thank you so much.